So I want to work out the Maclaurin polynomial of order 0 through 6 for cosine of x. I wanted to start this video, though, by writing out the general format for the nth Taylor polynomial centered at A. So the notation I'll use here, and I guess I'm going to start this way over here to make sure I have enough room. So the nth Taylor polynomial, the way we work this out is we start with, think n equals 0. So it's the 0th derivative, which we think of as just the original function, evaluated at the center, which is A, over 0 factorial, which is 1, times x minus a to the 0, which we're calling 1. Okay, plus first derivative evaluated at the center over 1 factorial, which is 1, times x minus a to the first. So we should actually write that. Okay. Second derivative evaluated at the center over 2 factorial x minus a to the second. Okay, and you keep going following that general format until you make it to the nth derivative. Okay, again, evaluated at the center over n factorial x minus a to the n. Okay, so now let's put some particulars on here. So in this example, I want to find the Maclaurin polynomial. So the Maclaurin polynomial of order 0 through 6. Maclaurin polynomial think of it as a specific case of the Taylor polynomial, but where the center is 0. Okay, so Maclaurin polynomial of order n equals 0 through n equals 6 for the function f of x equals cosine x. Okay, so this is the example we want to solve. So we could plug in 0 for the a's up here. Okay, and then 0 through 6, we'll worry about that in a minute. But so the general format here, let me go ahead and write this out for the order 6 polynomial, the very last one that we come up with, will be, so we're going to substitute 0 for the a's. So it'll be f of 0 plus first derivative evaluated at 0 times x minus 0 to the first, so that's just going to be x, plus the second derivative evaluated at 0 over 2 factorial x minus 0, which is just x to the second. Okay, and so on. I guess I'm going to do a dot, dot, dot on that, up to the 6th derivative evaluated at 0 over 6 factorial x minus 0, which is x to the 6th. Okay, and that's where we would stop if it's order 6. So that's the general idea. So what we're going to need are the first 6 derivatives of cosine of x. That's one thing that we're going to need. So let me write that off to the side here, I suppose. So if the original function is cosine of x, then the first derivative will be negative sine x. Second derivative will be negative cosine x. Third derivative will be negative sine x. So negative in front, and then the derivative of cosine is negative sine, so the two negatives will give us positive sine x. And then the fourth derivative of sine, we're actually back at cosine. And so with these sine cosine functions, you're going to cycle through the same 4 functions. I'll go ahead and write this out through the 6th derivative, but we're actually cycling through now. We're back to cosine. Next derivative is going to be sine. Oh, I'm sorry, negative sine equals negative sine. And then the 6th derivative will be negative cosine. Okay, now evaluate each of those functions at the center, which for Maclaurin polynomial, it's centered at 0. So f of 0 would be cosine of 0, which is 1. F prime of 0 would be negative sine of 0, which is 0. Okay, and so on. So second derivative, negative cosine of 0 is -1. Third derivative is sine of 0, which is 0. Fourth derivative is cosine of 0, which is 1. Okay, fifth derivative at 0 is negative sine of 0, so that's 0. And sixth derivative will be negative cosine of 0, so -1. Okay. So now I want to fill this in. We want to find the first, well, order 0 through 6. So I'll start with n equals 0. So P0, the order 0 polynomial for cosine of x, would be the sum, this sum, but stopping when n equals 0. So you're actually going to stop just with your f of 0, which is cosine of 0, which is 1. So our P0 polynomial is just the constant function 1. Okay, the order 1 polynomial, so P1, we would take the sum up to when n equals 1. So we would have f of 0, which is 1, plus f prime of 0, which is 0. So actually, in this case, P1 is just equal to P0. It's just 1. N equals 2. So the order 2 polynomial will be, so you'll take the sum up to n equals 2, which is here. So f of 0, which is 1, plus f prime of 0, which was 0, so we don't need to worry about times anything else. That's just 0. And then n equals 2. So second derivative is -1. So here, I guess I'll write this out. So plus 0 plus -1 over 2 factorial x to the second. So the order 2 polynomial is, well, I'll clean it up in a minute, but it'd be 1 minus x squared over 2 when you simplify it. Okay, the order 3 polynomial. So at this point, maybe you notice we could take P2, so which is the 1 minus x squared over 2 factorial, and just add on the n equals 3 term. Well, so the third derivative, f triple prime, is going to be 0. So times whatever else, it doesn't matter. It's going to be 0 for that product. So P3 is actually equal to P2 in this case. P4, we're almost there here, would be where we left off with P3, so 1 minus x squared over 2 factorial, plus the n equals 4 term, which would be fourth derivative, which is 1, evaluated at the center, over 4 factorial x to the 4th. Okay, with the fifth derivative, with the n equals 5 term, you're just going to add 0 because the fifth derivative is 0. So we don't really, that P5 is going to equal the same thing as P4 here. So I'm just going to put equals P5. So last one, I can actually fit it on the board here. P6 will be the sum where we left off. So 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Sorry, it's so small down here. And then the n equals 6 term is -1. So this will be, I'm going to have to erase the P4 for a minute. So this will be minus x to the 6 over 6 factorial, because it's the -1 times x to the 6 over 6 factorial there. So there, here are the first 4 Maclaurin polynomials for cosine of x. Now I've got them typed in nicely because I know it doesn't look, that might be a little hard to read where I have it written there. For the record, that answers the question that I had here. These are the first order 0 through 6 polynomials for cosine of x. But to give you some kind of meaning for that, I want to pull up Desmos. Whenever it decides to start sharing, just waiting. There we go. Okay, Desmos. And I've already got, oh no, I gave away the surprise. Turn these off. Okay, and unfortunately, there's no editing with these videos that I make with Collaborate. But anyway, okay, So I first entered the function cosine of x. So this is the function that we're trying to model with these polynomials. And we remember that we wrote the Maclaurin polynomials. So these are all centered at 0. So think of these as polynomial approximations of the function f of x equals cosine x. If it's centered at 0, our polynomial approximations are going to be most accurate close to 0. Okay, so there's cosine of x. Here's our p0 polynomial. So it does approximate the value of cosine of x fairly well when you're close to 0. You can see that there, but not real well once you get even a little bit away from 0. Okay, here's p2, which remember with the polynomials that we wrote, p2 is equal to p3. So this p0 was also equal to p1. This p2 is also equal to p3. Anyway, notice that, so that second order polynomial does model the cosine function better, does a better job of it. Again, centered around x equals 0. Here, if I bring in p4 in purple there, so notice that p4 is an even better approximation than p2, where p2 started to stray away from the cosine graph. P4 is kind of hanging in there, staying close to that cosine graph. And then p6 is going to approximate cosine over an even wider interval, about 0. So just this is the idea. And if we continue to generate polynomials, like actually, let me type in p8 here. So p8 would be everything we had here. So this is for n equals 1 through n equals 6. 7th derivative will be 0, but the 8th derivative will be positive 1, x to the 8th over 8 factorial. Okay, and so Desmos is using blue again, but notice that now that blue graph models the cosine function even better over this interval. And so the longer we're willing to sit here and generate terms for the polynomial, the better that polynomial is going to approximate the graph of the cosine function there. And that's what I have for you for this example.